Okay, so welcome back everyone and Happy New Year. So today it's my pleasure to welcome back Professor Mrozek, who will be giving the third lecture on combinatorial topological dynamics. Yeah, thank you, Marian.
Thank you, Boumediene. I think I should start with recalling a few main ideas from my last talk. So I defined a combinatorial multivector field on a finite topological space to be a partition of the cells of the elements of the space into locally closed subsets. So let's recall that a locally closed set is a set which is an intersection of open and closed set, and via the Alexandrov theorem, which says that every finite topological space is in functorial correspondence to a pre-order and T0 space to a partial order. So in the language of partial orders, a locally closed subsets is the same as a convex subsets with respect to the poset structure of space relation. I'll refer to these elements of the partition multivectors. And then I briefly mentioned that, in fact, this is a generalization of the Formann's concept of combinatorial vector field, because it's easy to see that both singletons and Formann's doubletons, so Formann's vectors, are locally closed in Alexandrov's topology. Then once I have such a combinatorial multivector field, I can associate with it a combinatorial flow, which may be viewed as a directed graph, where the vertices of the graph are just the cells in my so the elements of the finite topological space, but in most applications this finite topological space is just the finite collection of cells of a cellular complex. So I mark each cell, for instance, this cell here by its center of mass, this edge here by its center of mass. So this way I can view it as a directed graph, but I draw only these explicit arrows which come from the same multivector. So this collection is just one multivector here. This is another multivector in this partition. This is just a vector in the Forman sense. This is a singleton. But you remember there are also these implicit vectors which let you go towards the boundary from any cell. So you can always go to the boundary. But they are not drawn just to keep the picture simple, what is really necessary to understand the examples in the picture. So in principle, you can think about this dynamics as an action of a multivariate map, which sends a cell to anything in its multivector and to anything in the closure of the cell. The closure is just this. So this is a formal closure in this Alexandrov topology, but in terms of the poset of faces, it should be thought of as the collection of all the faces of a given cell. I gave the definition of a V-compatible set. So it's just if a this is the notation for the multivector to which X belongs. And then I say that a set is V-compatible if it has the feature that if a multivector intersects in a non-empty way, this set, then it's entirely contained in A. In other words, a V-compatible set is just the union of the multivectors it contains. And then there is a counterpart of this trajectory or solution for this combinatorial flow, and it may be just interpreted as this as a walk in this directed graph interpretation. So this map, by the way, this should be F. So this F defined here. So this is the collection of all targets of edges outgoing from vertex X in the language of the directed graph. And then a walk just requires that at each next step, you are at the target of an outgoing edge from the previous step. Okay, and once I have this concept of solution, I can speak about a solution which is internal tangency to a set. So if I have a set S and a solution which has values in the closure of S, then if I can find 3 points along the trajectory such that at the external points I'm in S, but the middle point is not in S, but still in a closure because the whole gamma, I assume, is in a closure, then I speak about an internal tangency. So this roughly corresponds to the situation which is forbidden if the Warzewski set, if you remember. So if this is a part of the Warzewski set, if the trajectory comes to the boundary and then goes back to the interior. And then I defined an invariant set is a set which admits a full solution through its element. So here an example of an invariant set is actually with this version of the combinatorial flow, actually it's easy to see that every set is invariant. This may look like a nuisance, but actually it's convenient for some other purposes, and I'll show in a moment a solution so that we can speak about so-called essential invariant sets, which correspond better to the classical invariant sets. So if I have an invariant set, I say that it's an isolated invariant set. If it's invariant, it admits no internal tangencies. So this behavior is excluded. Then there was also the concept of isolating neighborhood, a closed set N such that every path in N with endpoint is S is a path in S. So in particular, by the very definition, the closure of an isolated invariant set is always an isolating neighborhood, but there may be bigger isolating neighborhoods, and it will matter in today's talk. Later on, we'll see that it's sometimes convenient to consider many isolating neighborhoods. And then I recalled that in the combinatorial case, there is this theorem which gives a convenient characterization of isolated invariant sets in purely combinatorial language. So an isolated invariant set, is isolated if and only if it's V compatible and locally closed. Okay, and then I mentioned that actually, surprisingly, there is a nice characterization of attractors and repellers in this combinatorial setting, because the most important thing to remember is that unlike the classical setting, in this combinatorial setting, an isolated invariant set in general is not closed. And this is, roughly speaking, caused by the fact that we have no Hausdorff axiom in finite topological spaces. And this in interesting finite topological spacing. So everything is very tight, and isolated invariant sets have no luxury to isolate themselves from other sets in other way that they're just disjoint, but nevertheless they may touch one the other. But now, because of that, we get this interesting theorem that an isolated invariant set is an attractor if and only if it's closed, and a repeller if and only if it's open. So an isolated invariant set which is neither closed nor open will be neither attractor or repeller. It will have such a subtle type behavior. Okay, and then in order to define the Conley index, I mentioned that there is a kind of counterpart of Warzewski set in this combinatorial setting. Actually, it's modeled by a concept which plays a technical role in the classical definition. The concept of index pair is used in the classical Conley theory. And even here, to define the Conley index, we can go away with the definition, but we'll use index pairs later on. So maybe it will be clearer via the main result. Namely, for every isolated invariant set, regardless what are the details of the definition of an index pair, when you take the closure and the mouth, and maybe I should recall that the mouth of S is just the closure of S, take away S. Okay, so this is always an index pair, and it's a kind of canonical index pair for S. And in terms of the Conley index, you just take the homology of this, and this is the Conley index in the combinatorial setting. So in principle, nothing more is needed to define the Conley index. But to use it fruitfully, you need more. Namely, we will use different index pairs, which will give you also the Conley index. Why? Because actually, the analog of the other classical theorem is that if you have two index pairs, so maybe one, this canonical one by maybe another one, still when you take the relative homology of the pair, one and the other, you get the same homology, so they both give you the Conley index. So this theorem actually lets you define formally the Conley index as the homology of any index pair. And if you are only interested in the Conley index, then the easiest way is just to compute this relative homology and you get the Conley index. Okay, so this is in principle what I wanted to recall. And now a few new concepts. So I gave here a few examples of multivectors, and they may be classified in two ways. One way is the two multivectors on the left. They are just the vectors from Forman's concept of combinatorial vector field. So a singleton and a doubleton such that one element is phase of codimension one of the other. So these are classical, let's say, Forman vectors, and these are more general multivectors because you have more than two, 4 here, 6 here, 9 here, and 3 here. But there is other classification, which goes the top line and the bottom line. Namely, when you compute the relative homology of, so let's call the multivector V, and let's look at the homology, like in the Conley index, the closure of V and the mouth of V, this relative homology. So it is 0 in the top line and non-zero in the bottom and in the bottom line. Why? So you can actually use the geometric representation because of McCord's theorem, which I mentioned last time, to compute the homology. This may be the formal singular homology in the finite space. By the McCord's theorem, you can use the geometric representation, which is in the pictures. So here you take the homology of the triangle relative what is in the mouth. And it's easy to see that actually the triangle retracts to the mouth in this case. So the homology is relative homology is trivial. And the same here, this is the mouth and here is the mouth. In all these cases, the whole triangle retracts to the mouth, so the homology is trivial. Whereas in the bottom line, here the mouth is all the boundary, so the homology, relative homology here is the homology of a pointed sphere, so it's non-trivial. Here, the mouth is empty, so the homology is the homology of a point. And here, the mouth consists of two pieces, so the homology is the homology of a pointed circle. So again, it's non-zero. So I call a multivector V regular if this relative homology is 0. And a critical otherwise. Why such a distinction? In some sense, these regular multivectors have at least no topological condition which would enforce in the classical setting a flow to have a trajectory inside. So since everything retracts to the boundary, the flow may go through. There is no topological obstruction for the flow just to go through. Whereas in the bottom line, whatever you try to come up with so that your flow leaves through the boundary, you see that there's something must be inside. So in that sense, this is a critical multivector because by topological reasons, it has to contain already something inside. Whereas the regular vectors may contain something inside, but at least topologically, they are not forced to contain something inside. Okay, so this concept of regular and critical multivector lets me define the so-called essential solution. So I take now a solution, a full solution, and I say that it is essential if for all t in Z, such that the multivector of the point at the trajectory is regular, there exists t prime less than t double prime, such that at this point the solution is not in the multivector. So in a sense, I say that an essential solution just quits a regular multivector, cannot stay there forever. It can come back, but first it has to go out, like with the American visa. You can stay for some time, then you have to go back somewhere else, and then you are free to come again. But you cannot take a tourist visa, go to America and stay there until the end of your life. So for instance, when you look at this periodic solution, we already discussed this one. This solution is essential because although it goes only through regular vectors, these are just Forman vectors, but it always leaves each vector to another one and to another one, and then of course it comes back, but that's fine. You can come back when you just leave earlier. And this lets me define also S to be an essential invariant set. If every point there is a solution, a full solution in S, which is essential, and of course through X. So this is the remedy, just restricting our interest to these essential invariant sets to eliminate this feature, which is useful for some other purposes, that in fact every set is invariant, because you remember we are always free in the solution to go to the multivector of X and the closure. So in particular, we can stay in X, which makes every point a stationary solution. But such a stationary solution will be essential only if the multivector is critical. Otherwise, it will be an inessential solution. Okay, so with this concept, we can also now define gradient-like combinatorial multivector fields. So first, I say that an essential solution is recurrent if pre-image of any point for X in the image of this solution, if the preimage is unbounded. So a solution is recurring if the solution both forwards and backwards keeps coming back to this to every its point. And then I say that V is gradient-like, or simply gradient, if for every recurrent solution so the only way to have a recurrent solution is just to sit in one multivector. There exists a multivector in V such that the whole solution is in V. Why such a definition? You maybe remember I mentioned last time that in this definition, which I gave here, let me copy it. This multivector part is considered to be a kind of black box. So everything which is beyond the resolution we have in our data to distinguish the real behavior there. So we just do not want to forbid something which we do not understand the behavior. So the default assumption is to allow everything. But otherwise, once I want to pass from one multivector to the other, I can do it only via the closure. Like it would happen in the case of a classical flow line, to go from one cell to the other, you have to cross the boundary. Okay, so since this is this kind of black box, I will have recurrent behavior inside here. But if this is the only behavior, recurrent behavior, then that lets me call this multivector field gradient-like, at least gradient-like via the resolution I have via these multivectors, what I can see. Okay, I aim now to defining the Morse decomposition in this setting. So for this, I need limit sets. So first, some notation, maybe some terminology, VHAL. So I have now a set A. Maybe I write here. And I'll use this notation. The VHAL is the intersection of all subsets, all supersets of A, such that B is V compatible and be locally closed. And then I can, given a solution, a full solution it's alpha and omega limit sets are, I'll write alpha of gamma to be just this VHAL of the ultimate negative image. I'll define it in a moment, gamma under V, and omega the same. That I now put plus here. And what are these ultimate images? So this is just the intersection of the images of intervals from -infinity to t over -t, and analogously for the plus so I put plus here, and of course this will be now from t up to infinity. So it's very similar to the classical concept of limit sets. I have to define a limit set for a solution, not for a point, because of the multivalued nature of these combinatorial vector fields. In case of classical flow, once you have a point, there is a unique solution through this point, so you can speak about limit sets for a point. But here I need the whole solution. And roughly speaking, what you do is you just look for the recurrent part of the solution when you go forward for ultimate positive image, when you go backward for ultimate negative image. And this is not yet the limit set, because I want this set, the smallest V-compatible locally closed set containing these ultimate images. This is just needed to make sure that, as in the classical case, you have the theorem that always these limit sets are isolated invariant sets, alpha and omega or gamma are always isolated invariant sets. Okay, so now with the definition of limit sets, I can give the definition of Morse decomposition. So again, the analog of the definition I gave in the first lecture. And this is again quite similar. And the differences again come mainly from the multivalued nature of the case. So when I take a collection in P, P is in P, with P a finite poset. So such a collection is a Morse decomposition. If M is a family of mutually disjoint isolated invariant sets, and for every full solution either the whole image of the solution is in one of the Morse sets, or there exists P prime in our poset such that P is less than P prime, and the alpha limit set of the solution is contained in the Morse set associated with the higher index, and the omega limit set of the solution is contained in the Morse set associated with the lower Morse set. So in this example, I have a Morse decomposition which consists, if I remember well, of 6 isolated invariant sets. So let's look at them. One is just this critical multivector, a singleton, like in Forman. Here is another just one critical. Then there is a periodic solution here. We already looked at it several times. Another periodic solution is here. Actually, here you can go through, this is a huge multivector, consists of 6 elements. So this Morse set actually contains many periodic solutions because you are free to go anyway through this multivector. And then there is a third critical cell here. And there is this multivector is also critical, but it's not just a singleton. It's an example of a monkey saddle here. And now, okay, so this is a collection of disjoint isolated invariant sets. What is the poset here? I'll show it in the next slide, precisely the poset. Here, let me mention only one theorem. That if you just forget about the topology, and this is quite a surprising result, if you forget about the topology here and just treat our directed graph as a directed graph, because you remember that the essence of the theory here is that we look at things as a directed graph, but it's a directed graph whose vertices form a finite topological space. So in our examples, the vertices are just the cells of a cellular decomposition of a continuous space. But you can forget for a moment about the topology, and a directed graph has the family of strongly connected components. So the theorem says that the family of strongly connected components of the V graph, GV, this dynamical system interpreted as a directed graph, is a Morse decomposition. And in some sense, this is the finest Morse decomposition. If you are familiar with the concept, which actually I'll define in a moment later on, but it's one family may be inscribed in the other. So this gives a partial order on the collection of partitions of the set. And in that sense, this is the smallest possible partition, which makes it a Morse decomposition. Not necessarily the most interesting, but this case is different from the classical one, because in the classical one, this is just possible because everything here is finite. In the classical case, you can have finer and finer and finer Morse decomposition, so there is nothing like the finest one. Okay, so back to the poset, but maybe I change the slide. So here I have the poset structure. Every Morse set you maybe have noticed, I marked this both by different colors, but also by the different shapes. So for instance, this periodic trajectory as a Morse set is marked here with small triangles, and this is its position in the poset. This periodic trajectory is marked by small squares, diamonds, and its position here in the poset is in this place. Then we have this one with a circle, it sits here. This one with a black disk, it sits here. This saddle is here, and this saddle, this monkey saddle is here. What I've drawn here is the so-called Conley-Morse graph. Which actually is this poset with labels which are Conley indices. Conley indices written in a special form. So what are these polynomials here? Let me explain that. So the you remember the Conley index is just the easiest way to compute the Conley index of the ith Morse set is just the homology of the closure of the ith Morse set relative to its mouth. So this is by definition the Conley index of MI. But if you take field coefficients for the homology, for instance, Z2 coefficients to make things simple, but any field coefficients, then this homology splits into the grading according to each grade, and in every grade, you just get a vector space. So these polynomials here, which I call Conley polynomials, so PMI, the Conley polynomial of the ith Morse set in this Morse decomposition, is formally written this way as an infinite series, but it's actually a finite, always a finite polynomial, where you take just the dimension or rank. In case of homology, you typically speak of modules, even if the coefficients, when the coefficients are from a field, then they are vector spaces. I could write dimension here as well of the Conley index in, maybe let me take over Q, because I was used to index the Morse sets. So let Q use, gives me the grading. So the Conley index in dimension Q of MI multiplied by TI. So in principle, this is the way to gather the dimensions of the Conley index in the respective grades and written as a polynomial. So for instance, this Conley index, what does it tell me? That the Conley index is non-trivial in all, it's trivial in all the grades except grade 2. But this corresponds to this Morse set. Here the mouth is everything in the boundary. So when you glue the mouth to a point, you get a two-sphere, and the homology of a pointed two-sphere is non-trivial exactly in dimension 2. So this is why I get T squared here as the Conley index. The same here and here. This is just the simple computation. Maybe a few words about this one. So this is non-trivial in 2 dimensions. This is our periodic orbit here. The mouth consists of 2 pieces, this, and this is also in the mouth. So if you glue all this together, it's for some people quite straightforward. For some, maybe requires some concentration to see that this relative homology is the same as the homology of a wedge of 2 spheres, 2 sphere and 1 sphere. So this is why we get non-trivial homology in dimension 2 and dimension 1. And similarly for this one, here the mouth is empty set. So you get relative to empty set as a pointed, you get 2 connected components. One for the empty set glued to a point still gives you a point. So this is 1 point which is separate from the connected component of this one. And this gives you non-trivial ingredients in dimension 1. This is just this topological circle. And the dimension 0, which comes from the empty set as the exit set. And maybe this one, this is the monkey saddle. Here, the mouth consists of this piece, and this edge here. So 3 pieces in the mouth. So when you glue them together, you get a wedge of 2 spheres. So this is why you get here the coefficient of 2. Of course, for that to see 2, you need rational coefficients, for instance, because with Z2 coefficients, this 2 would be the same as 0. So then you will get Conley index 0. Okay, so this is the Conley Morse graph for the Morse decomposition, which I believe is of interest maybe less as in the classical case, because in the classical case, when you understand this Conley-Morse graph, you can deduce actually the existence of certain connections, heteroclinic connections between Morse sets. But in this combinatorial setting, I view it as a nice, very concise descriptor of the dynamics, which you can see in this otherwise complex picture. And we'll discuss in a moment persistence of Morse decomposition and Conley indices. So this may be investigated in similar spirit as in topological data analysis. Okay, so this is what I want to recall very briefly now. In order to move to persistence, very briefly, what is the persistence theory for topological spaces? The idea is presented in this picture presented here by permission of Robert Grice from this paper of him, which is a nice overview of the ideas of persistent homology. Namely, you think about a topological space, in this case, a simplicial complex, as built in steps. For instance, you have just a cloud of points, and then you believe that this cloud of points comes from actual topological space. You would like to understand the shape of this space. So you may say, okay, I have only a finite sample, but probably points which are nearby in the actual space, they just are in one connected component. They just are joined somehow. So what I can do is to pick up a measure, a certain measure, and glue together points which are close enough. But of course, the big question is, what does it mean close enough? Typically, it's not so easy to give a reasonable guess what is close enough. So instead, you keep varying this measure, and you get several topological spaces with the increasing measure. So this one is the minimal one, then I take a little bit more, so you get more things glued, and then a little bit more, and so on. And eventually everything gets glued, because now my measure is so big that every point is close to another point. And then I look how the homology changes through this process. And you may notice that there are some connected components which appear, but later disappear. For instance, you have a separate connected components here, but when you move to this picture, all this piece, and this piece are all glued together to one connected component. So in fact, two homology generators are killed in this process. Similar things happen to first homology generators. For instance, two cycles are born here at this stage, and they are still here, but when we increase the measure, this cycle, which was visible here and here, now disappears, because the points are close enough that I add just the whole tetrahedron here, which fills this space here, and so on. And this may be marked by bars, which indicate when a generator was born and when it disappeared or died, as they say. So this is for H0, this is for H1, for the first homology, this is for the second homology. Of course, these pictures should be considered as a projection onto the plane of a simplicial complex which sits in higher dimensions. So this is the so-called barcode. It may be also represented as a so-called persistence diagram, but barcodes for us will be sufficient today, which may be obtained from such a filtration of spaces. So because in principle, by varying this measure, I get a sequence, a growing sequence of spaces like here. So this is a filtration of spaces that actually it doesn't matter where this filtration comes from. It can come from varying measure, but it may come from various different sources. And you still get this barcode describing the behavior. What can you learn from the barcode? In the simplest interpretation, you just look for those bars which extend for a long time. So short bars are typically attributed to some noise, but long bars are probably more related to the nature of the space. In I know that in particular in machine learning, people use nowadays these barcodes without just looking directly by human eye into the barcode, but they are used as an input to some other techniques typical for machine learning. So first you take your data, you produce your barcodes, and then you analyze, instead of analyzing directly the data, you analyze the barcodes by the tools from machine learning. The last comment about persistence I want to make is that there is a generalization which actually allows these arrows to go in arbitrary direction. For us, the most interesting case is that actually you can take an arbitrary sequence of spaces and then take the intersections and the inclusion which goes, the intersection of x1, x2 included and x in x1 and in x2 and so on. This also leads to a barcode. And we'll see in a moment that this is useful in our setting, but maybe one remark. Of course, one could say what use could be out of it if you take just arbitrary sequence of spaces. Of course, the point is that even if there is not just a simple inclusion like this, you believe that you have a sequence of spaces where the neighbors are somehow related. So there is some small, maybe minor change, which does not just induce an inclusion. Maybe the inclusion is from the left to the right or from the right to the left, or even worse, there is no inclusion at all. But when you take the intersection, you can get something which is common in both spaces, and then you use the inclusion from the intersections to the two neighbors. And then you'll see if something persists via these small changes, which is not necessarily just addition. You may add something, you can remove something and still come to the barcode. Okay, so how to use these ideas in our context of combinatorial dynamics? So I need now these refinement concepts. So some notation. I'll refer to the figures in a moment. If I have two families of subsets, I'll use this for my multivector fields, but the definition works for any two families. I'll write that P is inscribed in W if and only if for every element in V, there is an element in W such that the V is contained in W. And then I'll also use the family of intersection with this notation. This is the family of V intersect W for V in the family script V and W in this family script W. In the context of multivectors, I say that a multivector field V is a refinement of W if V is inscribed in W. Equivalently, you can easily see each multivector V in the multivector field script V is WV compatible. And why are we interested? Just in the context of zigzag persistence, because we have the following proposition, easy to prove, that if you have two multivector fields on X, then if you take this family of intersections, you also get a multivector of fields. Moreover, this family is inscribed both in V and W. Okay, and this lets us define the persistence of Morse decomposition. But for that, I need a few more concepts. And the reason for these concepts is, again, caused by the fact that our space is so tight, only T0, and isolated invariant sets may not be separated as with the Hausdorff axiom one from the other, but will be disjoint, but still touching one the other. So I need an additional topology, which I call the Morse topology of a multivector field. I'll denote it TV. Is the topology. Of course, the topology is on our finite topological space X, but I modify its original topology by taking the topology with basis, which is just this family of intersections, namely the T is, I denote by T this Alexandrov topology, which I use on our collection of cells, and I intersect it with the Morse sets, with the family of Morse sets. These Morse sets associated with the Morse decomposition of a given Morse decomposition of V. And then you can prove the following proposition, that if you have this situation that one is a refinement of the other, then this implies that actually this topology of the Courser topology, the topology associated with the Courser multivector field is a subtopology of the topology, this Morse topology associated with the finer multivector field. In particular, this means that if that the identity on X, but acting on X with this topology on V, considered as a map to itself, but with the topology, Morse topology of W, this is continuous. And this fact actually, by applying now singular homology, immediately leads to zigzag persistence. So now I assume I have a sequence of multivector fields. And then I can just build this zigzag persistence by taking the homology on X with TV1. Then there is this identity induces, but with changing topology. So in homology, although it's identity as a map, in homology, this may be any linear map. The homology of the X with the topology associated with this intersection multivector field. Then you go to the homology of V2, and you keep repeating this process. This gives you a zigzag persistence module, so this produces a barcode. Okay, I'll give an example in a moment, but let me go back to this. I haven't discussed yet these figures. So here I want to explain this refinement and the intuition which is actually associated with the refinement. So look at this small multivector field here. It has only singletons, dubletons, and only one non-trivial multivector in the sense that it consists of 4 cells. And this one is actually a refinement of this one, because I actually keep the same partition, except I subdivide this multivector into 2 vectors. But there is another way to subdivide this one into vectors, like here. So actually, this multivector field may be refined both to this one and to this one. And the interpretation is that this refinement acts like a kind of counterpart of perturbation in the classical setting. So when you subdivide, you get similar but still different, a little bit different behavior. We'll go back to that example if time permits. Very briefly, let me mention that what happens in terms of dynamics is that in this example, there is a heteroclinic connection which goes from this critical cell via this multivector. And here we can go to the boundary, for instance, here, and then we can end up in this critical cell. But also we have a heteroclinic connection, which we go here to this multivector, and then for instance, here or here to the boundary here. But once I make this refinement, I kill one of the connections. When I take this refinement, there is no longer a way to build a heteroclinic connection from here to here, because when I go here, I have to go either. So my only option of interesting move is to go along this vector, and from here I can only go here. I am cut off I cut off the connection to this critical cell. When I do the other subdivision, I cut the connection to these 2 critical cells. Once I go here, I'm forced to go here, and from here only to boundary, so here. So this is very similar actually to happens in bifurcations in classical dynamical systems, and we'll see this again in a moment. So here is an example of application of this persistence of Morse decomposition in the context of building a multivector field from a cloud of vectors. I had no time to discuss what algorithms we use to build a multivector field from a cloud of vectors, but this is the typical situation where you want to apply this. So think about this, that you have this cloud of vectors, so a cloud of points, and every point a vector, classical vector in some high dimensional space, in this example in 2 dimensions. And then you somehow chose your cellular division, and then you want to replace this vector, which will probably go in some direction, not necessarily nicely aligned with edges. You should decide how to build your multivector. And then you have choices, and these choices depend. You would say, if this vector goes nicely into the middle of this triangle, then probably you would say, okay, I should make here just a multivector which lets me go anywhere here. But the other option, if you decide that this vector is actually close to one of the edges, then you may decide, okay, I should just build just a regular vector here, because this is a better approximation of this behavior. And again, here we have the same problem. What is the threshold? What is the angle? How should I decide? When should I flatten this to a vector like this? And when should I keep it as just a multivector like this? And like in my example, which I gave for the classical example of persistence, the solution out of it is to look what happens when you vary this angle. Just first you fix an angle as a threshold, and when you say when the angle is smaller than a given number, you flatten this and make it just an edge, a vector, Forman vector. But if it's far away from all the edges, I make it a multivector. But then you vary this threshold angle, and you look what happens when you study the Morse decomposition. And here is an example which was done by colleagues of mine for cloud of vector built out of Lotka-Vortela equations. So this is a planar system with a stationary point which is repelling and a periodic trajectory somewhere here. And these are the Morse, just 3 examples of zigzag persistence module. This is just a picture consisting of 3 samples, but actually, if I remember correctly, we went through like 50 values of this varying flattening angle in the construction. And we looked at the persistence of the Morse decomposition we got for these varying angles. And what you see is that somewhere here in the middle, we kept getting these spurious annuli, like this yellow one in the middle and the 2 violet ones. But what is expected here is should be just one Morse set which corresponds to the attracting periodic orbit, and one Morse set inside corresponding to the stationary point inside. There is this one here, but it's very small. It's in this resolution. It does not show up. It does show up here. Probably the color was chosen badly here, but we know from homology computations that it is here. So somehow the middle choice of the flattening angle was the worst one. And if you look at the barcode, there are these which you could attribute to the bad choice of the flattening angle, but the long bars are the one blue, which is for dimension 1, which corresponds to the first homology of this Morse set, and 2 yellow in dimension 0, which corresponds to the 2 Morse sets actually. Each gives a connected component. So this example shows that it actually gives you this mechanism of persistent homology, gives you what you want to get out of it. You just get rid of some spurious things which may be caused, in this case, by the bad choice of the flattening angle, but in general, even by noise. Okay, but this was about the persistence of Morse decomposition, but now I'd like to look into the persistence of the Conley index itself. This is a little bit more complicated. Let me explain it on this very simple example where with my simplicial complex is just this interval divided into 6 intervals. So I have 7 vertices and 6 intervals. This is my whole space. And let's say that I want to model a dynamical system which I expect to be just a repelling fixed point on the real line. So something like this is the classical flow I want to see here. And here is the representation I would get on this combinatorial setting. So my fixed point will be represented by a critical cell somewhere here. Maybe I should copy it from the previous picture. So this is the classical flow I want to model. And then I see just vectors, a vector here because I move here and so on here. And just to have everything invariant, I just added a fixed point here and here, which may also happen in the classical case. So I may assume that they're also attracting fixed point and the end point of the interval. But now imagine that there is a parameter in the system, and this parameter causes that my stationary point here just slowly moves in this direction. What will happen when I look at it via my discretization? Let me copy this again. So imagine that we moved it, that it's precisely over this fixed point. Then the only way to represent the dynamics is, because now my fixed point in the classical dynamical system is exactly at the vertex of my discretization. So the only way is just to make it a multivector which points in both directions here. So this is now my only multivector, so no longer a Forman vector field, because I have now a multivector consisting of 3 cells, 2 edges and a vertex. But when I continue and move further, so that was my situation. Now let's say this moves even farther. And now it sits over this cell. So I have again a picture which is similar to the previous one, but the critical cell is not here, not here. And the Conley index of this critical cell in every case is just T, because there is just one generator in dimension 1, because you can draw the index pair, which consists just of the closure of my isolated invariant set, which is just a cell here, and its mouth, and the mouth consists just of the 2 endpoints. And this is how it looks like here. Now my multivector has 2 1 cells and 1 0 cell. So the closure is just from here to here. And again, the endpoints are in the mouth. And here what I have is again similar to the first case. So the Conley index, the relative homology in all the 3 cases is the same. And what I would expect is that somehow I see a continuation of this isolated invariant set just moving in space to this position. And in that sense, I should treat this as just a continuation of this one, and this as a continuation of this one. So in the barcode, I would expect to just see one bar which extends. This is a varying parameter in the space, extends from here up to here. But my technique with the intersection does not work, because the intersection, when I intersect this index pair with this index pair, what I get is, by intersection of pairs, I mean intersection of respective elements. So I intersect the green sets, which will give me, maybe I draw it here. So this will be the smaller one, but now when I intersect the red ones, so the mults, then I got only this here. And this actually is not the right Conley index. So I would not expect a generator of homology to go from here to here. And it looks like a serious problem, but actually this is related to the fact that although in the combinatorial setting there is this finest index pair, by the way, this is not only that the homology is wrong, but actually I did not go through the definition of index pair, but if you try to check, this is not an index pair at all. It does not, the intersection here does not satisfy the feature that if you intersect two index pairs, you still get an index pair, whatever the definition is. This is no longer index pair in this case. And this is because we just wanted to use, in every case, the smallest index pairs. And we remember there is a choice. We can have other index pairs. And this is the remedy, actually, because there is a modified concept. Namely, the idea is just to look for something which happens in a fixed isolating neighborhood. The point is, and maybe I draw it here with a different color. The point is that all these three cases have a common isolating neighborhood. When you take this big interval, it's an isolating neighborhood for all three cases. This isolating neighborhood isolates this isolated invariant sets, this for this multivector field, and this for this multivector field. So the point is to modify the concept index pair to relate it somehow to a common isolating neighborhood. And here is the definition. So I assume now that N is an isolating neighborhood for an isolated invariant set S. And if I have a pair of closed subsets of N, such a pair is an index for S in N, and this now matters, this in N, if I have three features, and they are, when you look in the previous definition, they look quite similar, but now the N is involved if you speak about an index pair, there is no need of N. I thought that maybe I have time to explain the intuition which is behind this definition, but unfortunately it's not the situation. So let me go briefly through this. And the last most important feature is that the S is just the invariant part, the maximal essential invariance set in the difference. So this is exactly the situation. When you take this N and as an index pair, actually, in this simple case, you can take as an index pair just a common index pair in all the cases. It's not so good in every situation that you can take a common index pair, but in this case, yes, you can. And this is an index pair in this yellow isolating neighborhood for all isolated invariant sets. The maximal essential invariant set for this multivector field is just this cell. For this is just this cell, but for this, you have the maximal one is just this multivector consisting of all those three. Okay, it's not so good, as I said, that you can always find a common index pair when you make this perturbations. But nevertheless, you have the following theorem. I assume N is an isolated neighborhood for S under V. So I have an isolated invariant set for the multivector field V. And I also assume, and probably now it's again useful to copy and modify. At the same time, I have another multivector field W and another isolated invariant set T. And moreover, I assume that P, maybe I denote the pair just by one character. P is an index pair for S in N, and analogously, I have another index pair which I'll call Q. So again, Q is Q1, Q2, but just written as, and this is for T in N. Then all this implies that if I take the I need a little bit more space. Let's shrink this a little bit. And I take Q1 to be the intersection of, R1. And R2 to be the intersection of P2, Q2. Then N is an isolating neighborhood for the maximal invariant set in R1 minus R2. Under the multivector field, which is both refinement on V and W, with index pair with R as index pair in N. So via this theorem, you actually can set up a zigzag persistence, because now you can write something like P1, P2, and this R1, R2 is an index pair, not for V, not for W, but for this refinement of both. P1, P2, R1, R2, and here Q1, Q2, and so on. So here is an example from Hopf bifurcation, figures prepared again by one of my co-authors. So I just take bifurcation where I start with an attracting fixed point. This is already a cloud of multivectors obtained from the associated differential equations. There is a parameter there, lambda. When lambda is much less than 0, then we see an attracting fixed point. Then a repelling fixed point, and then we see a small periodic trajectory born, which keeps growing. Here it's more or less in this place when lambda grows, and eventually it leaves the square when we make the observation. So here it attaches the boundary, and eventually it goes out. Now it's no longer contained in the square, so we cannot see anymore a periodic trajectory. We are left with just the attracting fixed point inside. So when you just build these multivector fields out of these clouds of vectors, so this is the enlargement of the picture, you actually do get this, the regular triangulation and the multivectors, which sometimes look like this, sometimes like this. This is based on one of our techniques of building these multi-vector fields. So then you see this, this attracting fixed point first. So the Morse decomposition just has one element, and then, and then it keeps growing because there is a periodic trajectory born, but the maximal invariant set here contains not only this periodic trajectory, but also the fixed point inside and all the connections. And as it keeps growing, it eventually will leave, will grow big enough to go out of the square. So at this stage, the maximal invariant set inside is again only the fixed point because the periodic trajectory went out of this. But this red piece here is just to show that if you look through the exactly the same strategy of looking at index pairs, which you could draw here, they are not drawn, but because actually the exit set is empty all the time because this periodic trajectory is attracting and you take everything inside. So the exit set is empty, but suddenly this is still an isolating neighborhood. And this red piece together with blue makes P1 of an index pair where the P2 is just the red thing. So this is an index pair which is now no longer for the attracting fixed point, but for the attracting periodic trajectory, but for the fixed point inside. And this is reflected by the barcode now computed of the Conley indices. So up till here, you see just one bar in dimension 0, which corresponds to this attracting disk here. And it stops here, and here there is born a generator in dimension 2, the blue bar, which corresponds to this maximal invariant set, which is this repelling fixed point. Okay, so here is another example, both in the classical version and in the purely combinatorial version. What I want to explain on this example is the situation when you have two saddles. So there is one saddle here, another saddle here, and there is a parameter which causes that these saddles move a little bit in the space. And I have a discretization which goes through these triangles in this case, which lets me build a multi-vector field here. So here I observe an isolated invariant set, and I can try to follow it as the situation changes. So they correspond. So this is an isolating neighborhood for which corresponds to this fixed point, but it's an isolating neighborhood as the closure, but an isolated invariant set with remove the mouth because things go out here and go out here. So you see the Conley index of a saddle because so generator non-trivial non-trivial generator in dimension 1. And when we modify the system, this now shrinks a little bit this combinatorial representation, but this is the same Conley index because the mouth, the exit set consists of two pieces, but we come closer and closer to this other fixed point. And in this discretization, although in the flow I still see two distinct fixed points, if I have only this approximation, I cannot tell what's going on here from this resolution. I only can say that I have an isolated invariant set whose mouth consists now of three pieces, this piece here, this piece here, and this piece here. So now I see a bifurcation on the combinatorial level, although there is no bifurcation in the flow level. Nevertheless, the reason I see the change of the Conley index, which may be actually captured exactly by these bars. This is the persistence bar obtained via this zigzag method with these index pairs in a fixed isolating neighborhood, which in this case is actually, yes, oversimplified a little bit because of lack of time, the fact that actually you use the fixed isolating neighborhood to look for the persistence only for short steps, but then there is a way to modify isolating neighborhoods. So if you are a fixed multivector field, then there may be many isolating neighborhoods for the isolated invariant sets. So you can change also the isolating neighborhood. So in this example, I actually, because this is only a selection out of 3 most interesting of a much longer sequence of multivector fields. And here in between, I had also to change the isolating neighborhood to continue what's going on. But nevertheless, going to the point is that although there is no bifurcation in the classical sense, what I see here is that I could notice here 2 saddles, but they come close enough together that with this resolution, I cannot distinguish these 2 nearby saddles from just one saddle, one monkey saddle. So what I get here is a Conley index of a monkey saddle. So actually, this Conley index let you also detect bifurcation-like behavior. Bifurcation-like because if you are only based on data, you can never tell precisely what happens, but you can make at least reasonable guesses that something close to the monkey saddle bifurcation happens. Okay, so I think I used most of my time. I had ambitious.
Can you try again?
Sorry.
It's all good.
It's my watch who tries to speak to me. Sorry for that. Okay, so let me go just to conclusions because I used practically all my time. So here a few concluding remarks. So as I tried to explain from the very beginning, the whole purpose of this combinatorial dynamical system is to take a shortcut from data sampled from a dynamical systems to this finite topological concise descriptor like Conley index, Conley Morse graph, and connection matrices, which I had no chance to explain, but they are about algebraization of these Conley Morse graphs. There is a nice algebraic theory which explains this Conley Morse graphs in an algebraic language. So this combinatorial dynamics serves as a two-sided bridge between finite and continuous mathematics. This is another topic I had no time to explain, but actually from the combinatorial dynamical system, you can build a classical one with the same Morse decomposition and vice versa. There are discretization techniques which let you even construct computer-assisted proofs via this combinatorial multivector fields. And this resulting correspondence covers gradient of recurrent dynamics. And again, if you're after gradient dynamics, actually it's enough, at least to find the Morse decomposition, it's enough to forget for a moment about the topology. Take just the strongly connected components of the V graph, and then go back to the topology to understand the Conley indices and the associated dynamics, whether they are repellers, attractors of what kind of saddles. But you can do the same also with recurrent dynamics. So a chaotic, periodic, that would have to be just a subject for another talk, how we do that. And they provide concise global descriptors of sample dynamics without the need of constructing an ODE or other analytical models. And the last thing I explained today is that this descriptor may be studied by means of topological persistence. So here is just a collection of references which cover the topics I discussed during these 3 lectures. So thanks a lot for your attention. Thanks a lot that you followed me up to this point, and I'm ready to answer questions if there are some.
Yeah, thank you very much. Thank you. Any questions or comments? Yeah, we can't hear you. I think we so you are far.
Hear me better now?
Yeah, this is better. Yeah, thank you.
Better now, yes.
Better. Okay. So this can be a very ignorant question. When you did refinement and there was an intersection,
Yes.
I just feel, what if there is no intersection? How do you do refinement?
There is, okay, so let me go, maybe I find it another way to get it quicker to this definition. Where was that? One moment. It was somewhere here. Yes. So this is how the family of intersection is defined. So actually, if V is a partition and W is a partition, I should say here you take the family of intersections, which of course you do not want to take empty sets, but nevertheless, you can show that if V is a partition of X and W is a partition of X, then the family of intersection is still a partition of X. So it's not the situation that everything is empty, and actually the same with the index pairs. With the index pairs, yes, with the index pairs, it may happen that still the two index pairs give you one or even both of sets to be empty, even if you do it in N. But that would only happen in the situation when you try to understand relation between two combinatorial vector fields which are actually very far away. When you take a completely different two multi-vector fields to completely different two isolated invariant sets, formally you can still ask what persists from one side to the other side, and you'll see that nothing persists. If you get empty intersection, this will be visible. There will be no long bars in the barcode. And this will just tell you that what you tried to look at has no relation at all. This is, I know this is a little bit unintuitive, because in the classical setting, when you think about the continuation, you already have something which continuously changes. So this continuity is already embedded in the definition. You change a continuous deformation. And here, which still puzzles us, because I would not say that I really understand, I only see that it works, that's the point, but somehow I'm still a little bit puzzled that when I speak about the combinatorial multivector field and this multi-valued map F generated by it, it has no continuity features at all. But nevertheless, things work. But if you go to continuation, this continuation in the combinatorial case, it's also discrete in nature, which actually lets you try to compare things which are very far apart or not related at all. And then you'll get these empty sets, and then the barcodes will say you what you should expect. If you try to relate unrelated things, then you see nothing in the barcode.
Okay, you hinted that the isolated neighborhood set may vary in time, but will never lose its isolation property?
Yes and no. So in the classical Conley theory, there is a continuation theorem which says that as long as you keep an isolating neighborhood, the Conley index will not change. And in using this, you can actually follow an isolated invariant set. And the same happens here, but we have something extra which we do not know how to do in the classical setting, because doing the persistence in the classical setting is difficult from the very beginning, because the whole machinery for persistence from the very beginning is combinatorial. So it's not clear how to just directly discretize in other way than we do it via this combinatorial multivector fields. So what happens here is that actually you can jump from one multivector field to another multivector field so that even the Conley index changes. And there is, since everything happens in these discrete cases, there is no moment in between, like in the classical case, that if you want to see the change of the Conley index, you have to go through the moment and the isolation is lost. And this is why in the classical case, you can have this continuation theorem. As long as you have isolation, the Conley index is the same. But if you see a different Conley index, it means that for a moment, at least for one point along your path, you lost isolation. But now in this combinatorial setting, we jump. There is no continuous time, we jumped. And you are allowed to jump from anything to anything, which may mean that actually your isolated invariant set will change its Conley index. But it is like the way I think about it, you jump over the discontinuity which causes the lack of isolation, but you do not see exactly the case when there is no isolation. You just see it via the change of the Conley index. And this is why we could extend this concept of barcode for the classical setting. If you did in the classical setting the barcodes, they would just extend from the very beginning to the end, because you see the same Conley index, nothing changes. So you would have these long barcodes, and the change of the Conley index would be via the moment when the Conley index is not defined at all. And now we jump, but the way we see the change is via the change in the barcode, actually.
Okay, very nice. Finally, you mentioned the gradient dynamics, and since we do machine learning, it's natural to ask, what about gradient descent? Can you see that in your analysis?
Well, again, yes and no. So in some sense, yes, because these vectors which are outside of the Morse decomposition give you the information about the direction of the gradient. But of course, it cannot be so precise as in a classical setting. This is just a direction. So you have then a regular vector, because when you have a Morse decomposition, that everything which is outside of the Morse sets will be a regular vector. So for instance, you may have a regular vector like this with this mouth, or a regular vector like this. And this gradient information which sits here is that the gradient direction, negative gradient, of course, because we think about things decreasing along trajectories, will be going here, which could be also here and here, but definitely not here. That would be opposite gradient. And here the opposite gradient would be only this, and going through the mouth would be going in the gradient direction. So you get some value concept of gradient, which is not as precise as in a classical setting, but yes, there is a kind of analog.
So it's qualitative, not really.
Yes, yes.
Okay, excellent. Thanks.
Yeah, there's a question on the chat. So Alex, you can ask her directly.
Let me look at the chat. Oh, do Hodge Laplacians show up at all? This is something we haven't looked at yet. Nevertheless, my gut feeling is that the answer is yes, but it's only based on my limited understanding of the theory in this direction. This is in our plans to get a really good understanding what happens in this combinatorial setting. But from what I understand so far, yes, I think they show up.
Other questions or comments? It seems not. Yeah. Okay, thanks, Marian, again for this nice lectures, and then you are welcome to give 2 extra ones if you say if you want about the 2 other subsequent cases, whenever you want to. Yeah.
We'll see. Definitely not in the near future because we have a break now, and I promised some time to family. But if you're not bored and still interested, we can discuss it later.
Yeah, exactly. No, there is no rush. Yeah, thank you very much. Yeah, thanks again. Thank you.
Thank you very much.
Thank you.
Thank you.
Yeah, thanks. Bye-bye. Thanks.
Bye.